Thank you, and good evening, Gaia lovers. So yes, this is a short talk, no more than 2 or 3 hours at most, on the ABC of stars and galaxies, and another short talk a little later this evening. So this is about how the universe has ended up the way it looks at the moment. The ABC of stars and galaxies. I call it the ABC, not because I'm trying to make it really simple, but simply because when I thought about it, 3 of the most important factors as to how the universe ended up the way it is based on the A, B, and C, which I'll come to in just a second. When we look into the universe, we see trillions of galaxies, many of which contain maybe hundreds of billions of stars. The galaxies all look rather different. Some of them are isolated, some of them are close to neighbors and seem to be a little bit distorted. Some are beautiful spiral shaped with lots of spiral arms, and some look a little different. It would be nice if we understood where all these galaxies came from and how all the stars that make up these galaxies were born. And I figured that the easiest way of explaining that is to think of 3 factors. Accretion, meaning the coming together of lots of matter in the early universe. I'm not going to talk about how the universe was created, but some 14 billion years ago, we believe the universe came into existence. It didn't take very long to make all of the hydrogen gas, which ultimately fuels all of the stars in all of the galaxies. So accretion is the process, the accumulation of matter under the influence of gravity, and we'll see a simulation of that shortly, whereby gravity pulls stuff together and forms an early galaxy. One thing we don't quite understand is what's going on in the centers of galaxies. We've got a better understanding than we had 10 or 20 or 30 years ago, but it's still not exactly clear. But it does look like at the center of every galaxy, there's a huge, absolutely vast black hole, a so-called supermassive black hole, from which light itself cannot escape. Did the black hole form and then the galaxy grow around it? Did the galaxy form and then a black hole form at its center? These are questions that we're still trying to answer with some of the telescopes and observatories that I'll be mentioning in the second talk later this evening. Some black holes are eating a lot of the matter around them. Some stars are falling into these black holes. The black hole at the center of our galaxy is rather quiet. No matter appears to be falling into that particular black hole. And the C of the ABC is collisions. It might sound very dramatic if one galaxy collides with another, but we think actually collisions of galaxies are a rather important part of galaxy evolution. They wouldn't end up the way they look now unless galaxies have collided in the past. And again, we'll see a little bit of that later. So if that's the ABC, mainly the ABC of galaxies, but galaxies are made of stars. How do you make a star in the first place? Well, you might think it's rather difficult to make a star, but actually I would argue that it's actually easy to make a star if anybody wants to try this at home. All you do is start with an enormous cloud of hydrogen. That's perhaps the most difficult bit. If you start with a large enough cloud of hydrogen, and lots of it was made in the Big Bang 14 billion years ago, all you need to do is to follow these 3 steps. A is wait, B is wait some more, and then C is just wait a little bit longer and you're done. Basically, if you've got a lot of hydrogen and gravity is pulling on that hydrogen cloud and collapsing it, you will end up with a star. So in other words, stars are inevitable. Once you make a lot of hydrogen gas, as long as you're patient and wait a few million years, you will get stars. You don't have to have any special arrangements, if you like, to make stars. Then you have to say, right, how do these stars get together in galaxies? Well, okay, we'll have a look at that very shortly. Don't worry about all the detail on the left-hand side here. The only point I'm making here is that we can't understand everything about the universe just by looking at it. We can watch stars, we can look at galaxies, but of course, on a human timescale, we can only watch stars and galaxies over a very short period of time. We can't watch them for 1 million years to see what they do. So in order to understand why things are the way they are, we need computer simulations. Over the last 10 or 20 or 30 years, there have been a lot of computer simulations, all of which are trying to understand how stars form, how galaxies form. In other words, we put the relevant bit of physics into the computer program, that there's this much mass in the universe and gravity pulls stuff together, and we know sort of how stars work. And then we look to see what the computer simulations are telling us. And we ask, do the results of this computer simulation look anything like what we actually see in the universe? In which case, if it does, maybe we're getting a good handle on how things work. So again, I'm not going to go all the way back to the Big Bang, but just as a mind-blowing statement, we know that the universe is expanding. Everything appears to be getting further and further apart as far as distant galaxies is concerned. So that would imply that everything used to be a lot closer together. And if we wind the clock back about as far as we can deduce that everything that we now see in the observable universe, all of those tens of billions of light years across, all of those trillion galaxies, each of which contains 100 billion stars, all of that stuff used to be a lot closer together. And if we go back far enough, everything that we now see in the observable universe used to be a few centimeters separated from every other piece of the universe. In other words, you could fit the entire universe that we can see today into a golf ball. Now, it's rather difficult to imagine just how much stuff you would need to cram into that golf ball, but as far as we can tell, that's how things began. Not only was the universe the size of a golf ball, but it also had dimples, which is why this analogy is so good. The universe had small variations in density, so they weren't dimples as such, but they were small variations in density, much like the surface of a golf ball has some small variations in it. If we run a simulation and let's take a large amount of hydrogen in the early universe and let gravity do its stuff, what happens if we watch it for millions of years or a fraction of a billion years? The answer is these small variations in density get more exaggerated. Some areas get really dense. White here means much more dense. Black means much less dense. So simply by letting gravity do its stuff, it looks like the universe ends up with a sort of filamentary structure, a cosmic web, if you like. Now, the webs and these dots are not stars. They're much, much bigger than that. They're not even galaxies. Most of these white blobs are collections of galaxies, clusters of galaxies. So when we look out into the universe, is that what we see? Well, generally speaking, yes. I showed you some pictures of relatively nearby galaxies, but if we look even further out, we find the galaxies in most of the observable universe are not scattered at random. They appear to follow this web-type structure. There are filaments, there are lines of galaxies. Where filaments cross each other and join, it looks like there's a large number of galaxies. So they're not uniformly spaced, they're dotted in a particular structure, a web-like structure, which does indeed appear to be the case when we look out into the universe. So we have some belief that these simulations are telling us about how the universe has come to look the way it does. But if we want to simulate a particular galaxy, again, don't worry too much about the details in these images. If we want to simulate how a galaxy comes to be, it's not just a question of start with a lot of hydrogen, let gravity do its stuff. Because in the process of compressing the hydrogen, we are going to make stars. We'll see a simulation of that shortly. But once we start making stars, stars can be born, stars can live, stars can die. When a star dies, which it might do as a supernova explosion, it will start pushing stuff out. So although gravity is trying to pull everything together, when you start making stars and stars die, the radiation from those stars can start to push outwards. So if you like, it's a battle between gravity pulling things together and the results of dead stars pushing things out. So all of that has to be taken into account. Gravity trying to pull things together, supernova and possibly black holes, rather oddly enough, also produce radiation which pushes outwards. Not only do we have to take that into account, but it's rather embarrassing to admit that physicists don't really understand what the universe is made of in detail. We know there's lots of stuff out there in stars, in galaxies, but it appears that a fairly major content of the universe is this rather weird stuff which we call dark matter. Stuff that we don't really understand what it's made of. We know it's out there because of the effect it has on other matter. In much the same way you can't see the wind, but you can see the effect that wind has on trees. So the fact that trees are blowing backwards and forwards tells you that the wind must exist. Same idea with dark matter. We think it's there because of the effect that we can see it's having on other matter that we can see, like stars. But we don't actually know what this weird dark matter actually is. But it has to be taken into account when we're trying to work out how gravity is trying to pull everything together. So if we think of this particular part of the simulation, remember this white blob here is simply an area where gravity is pulling the hydrogen together and starting to form galaxies. And we think that what's happening is matter is flowing down these filaments and condensing or collecting in these little hotspots, these little knots where the filaments join. And we can look in detail at a simulation. We're now looking at not an entire chunk of the universe. We're looking at just what's going on in the neighborhood of one early forming galaxy and asking what's going on. So we think matter is falling in from the outside and collecting in this central region. The more yellow, means more dense. The darker the color, the less dense. So perhaps you can see that matter is falling in from above and from the bottom left and from the bottom right, and it's collecting in the center. You notice that the matter doesn't all just go to a point. It starts to produce a sort of circulating system, a bit like a hurricane or a cyclone, or a bit like water trying to go out of your bathtub. It's circulating and producing very high densities and very high temperatures. This is where stars will be born, and you can see that we're already getting something that looks a little bit like a galaxy, simply from having matter fall in. You notice that we're now getting very dark in the edges, meaning a lot of the hydrogen is getting used up and is collecting in this region, producing this sort of spiral pattern. And by running these sorts of simulations on lots and lots and lots of galaxies, we get an idea as to whether this is a typical way they form or whether or not different galaxies form in different ways. But we know spiral galaxies are out there. We have loads of examples. This is a picture taken with the Hubble Space Telescope. We have lots of examples of galaxies imaged with telescopes on Earth and telescopes in space, and we know that this particular type of galaxy is very common. It's not the only type of galaxy, but perhaps we can now understand how this type of galaxy forms looking at those simulations. Notice that we've got a lot of white, which is produced by stars in the spiral arms. Notice also we have a lot of splodges of pink. Pink is the characteristic color, or at least the red end of the spectrum, is the characteristic color that hydrogen produces. If you take hydrogen and make it a little bit warm, it will glow, and it will glow with the color red. So whenever we see a little bit of red when we look out into the universe, our first thought is that's probably a clump of hydrogen, a cloud of hydrogen. And these clouds of hydrogen that we see in this galaxy are basically stellar nurseries. There's one stellar nursery fairly close to us in our own galaxy. This is the Great Nebula in Orion. For those of you who have ever looked out on a winter's night, it's probably about to rise at the moment. Orion, the three belt stars, below the three belt stars, the sword of Orion is this. It is a hydrogen cloud in which stars are being formed. Right at the heart of this hydrogen cloud, stars are being born. And we can get an idea of how that works, again, by running a simulation and asking, well, if we take a large cloud of hydrogen, that might look like a star or a planet, but no, this is a large cloud of hydrogen. If we start with that and ask the computer to run forward a few million years and let gravity do its stuff, as long as we put in a small variation of density, so it's not perfectly uniform, it probably looks it, but if it's not perfectly uniform, then when we let gravity do its stuff, we find that, again, some areas become more dense, some areas become less dense as gravity pulls things together. The yellow is higher density, higher temperatures. If we allow this hydrogen cloud, let's zoom in a little bit so we can see more detail. If we allow this hydrogen cloud to collapse under gravity, it gets hotter and hotter in the middle regions. Eventually, it gets hot enough for nuclear fusion to occur, which means take atoms, take the nuclei of atoms, fuse them together, it releases energy. And so these little white dots that look like a popcorn machine, these are stars that are being born because the hydrogen has been compressed enough in this central region to generate stars. Notice that some of the stars stay roughly where they're born, and every once in a while you find stars that are made and end up getting kicked out of this particular region. So in other words, when we make a whole bunch of stars in this way, quite a few will stay in this collection, this so-called cluster of stars, but quite a few will be lost. We've just zoomed out and rotated round so that we can see a lot of the hydrogen has now been depleted. We're now black in the corners, but we haven't used up all the hydrogen, even though we've made maybe 1,000 or 2,000 stars in this particular collapse of this hydrogen cloud. We still have some hydrogen left over. In other words, there's enough hydrogen left over for other stars to be born. So we can ask ourselves, if this was a simulation, starting with a lot of hydrogen, then we end up with a lot of white dots that look like this, is that anything like the sort of star clusters that we see when we look out into our galaxy? And the answer is yes, because when we look into our galaxy, we find areas where there are, again, clusters of hundreds, if not thousands of stars. It's very likely that our sun was born in a cluster like this, but for some reason or another, our sun was kicked out of the cluster, because at the moment, our sun is on its own. It doesn't appear to be part of a much larger cluster within our own galaxy. So remember, when clusters are born, when lots of stars are born, some of them will stay put and end their lives close to the cluster they were born in, but our sun appears to be one of those that was kicked out, and we can't now identify which particular cluster we came from. That was billions of years ago that our sun was born. We can't now figure out we came from that cluster and now we're some distance away. Basically, 4.5 billion years is just too long to track back the sun's history. But all stars are born and live and die according to a set of rules, and one of the strongest rules, if you like, one of the most important as far as a star is concerned, is the idea of balance. Because gravity is always pulling, gravity never pushes, gravity is pulling stuff together, so any large star, the gravity of the star is trying to crush it. But because as soon as it gets hot enough in the center of a star, we start fusing hydrogen together, fusing hydrogen to make heavier and heavier elements, that releases energy. So at the center of a star, there's a nuclear engine, if you like, and that pushes outwards. So gravity is trying to make the star smaller, and the nuclear fusion at its core is effectively pushing out, trying to make the star larger. And every star is a balance between gravity pulling in and radiation pushing out. And when the opposing forces, gravity and radiation forces from the core, when they're balanced, then the star is stable, the star is happy. That's the state our sun is in. Our sun started burning, or rather fusing, its hydrogen billions of years ago, and there's enough hydrogen for it to continue doing that for billions of years. In other words, as far as our sun is concerned, gravity is in perfect harmony with nuclear fusion pushing outwards. As long as those two forces are in balance, the star is stable. But if for any reason those get out of balance, the star must change. In other words, when a star comes to the end of its life, it runs out of fuel, it's no longer producing the energy at the core, the radiation pushing out is no longer enough to counteract the gravity pulling in. So the star is going to change its size, it's going to shrink as soon as the fuel starts running out. Indeed, all aspects of star birth and star life and star death can be modeled by thinking about the opposing forces of gravity pulling in and radiation pushing out. When we're thinking about stars, it helps to think about where stars are on this particular diagram. It's a diagram in which the brightness of the star, how much light it produces, how much electromagnetic waves, how much light, infrared, ultraviolet, all sorts of light, how much is produced, with very luminous stars at the top and very dim stars at the bottom. The horizontal scale is effectively either the temperature of the star or the color of the star. It's the same thing as far as a physicist is concerned. Our sun is there, roughly in the middle of the diagram. For convenience, we talk about how bright is the star relative to the brightness of the sun. So by definition, the sun has a luminosity of 1. That's just a convenient unit to use. And the surface temperature of the sun is about 6,000 Kelvin, or about 6,000 degrees. And if we want to know how stars change during their life, it's helpful to plot where a star is by looking at its brightness, looking at its color, and figuring out where on that diagram does the star actually sit. So we can follow the life cycle of a star by saying we start with a large cloud of hydrogen, we let gravity do its stuff, and it pulls that hydrogen cloud together, and it can make quite a few stars out of one cloud. For instance, it might make a star like our sun, relatively small compared to some of the larger stars in existence in our galaxy. When the fuel in our sun eventually runs out, which will happen in a few billion years, then remember the balance of forces, things are going to change, it's going to contract, it's going to heat up, it's going to expand again. Lots of things are going to change because the forces become out of balance once the fuel starts running out. We think what is going to happen in a few billion years is the sun is going to lose the outer part of its atmosphere. It's going to swell up as a so-called red giant star. Some of that outer atmosphere of the star is going to be lost, and what is left after we lose the outer part of the star, what's left behind is a small hot object called a white dwarf. This object here is, perhaps you can read it, it's called a planetary nebula, nothing to do with planets. That's just an archaic name left over from the fact that when these objects were first seen centuries ago, people thought they looked a little bit like a disk of a planet. They didn't quite know what they were. But a so-called planetary nebula is a large cloud of hydrogen and other elements, which is the result of the outer part of a star blowing off the outer atmosphere and leaving behind a very hot core of a white dwarf. If we think about this star here, red giant, and if we think about that star there, a white dwarf, we can identify where they are on this diagram, because a large red object, it's large, so it's quite luminous, so it's higher in this diagram than the sun, but it's redder, it's cooler, it's further over to the right-hand side because it's redder. Whereas a white dwarf down here, it's not so luminous, so it's a bit lower on the diagram, but it's much whiter, much bluer, so it's further over to the left of this diagram. So when we see a particular star in the sky, if we find its luminosity and we find its color, we can get an idea of where it might be in its life cycle once we understand, for instance, what's happening to our sun. But a cloud of hydrogen won't necessarily make small stars like our sun. It might make very big stars as well, very massive stars. A very massive star will use up its fuel much more quickly than our sun will, and again it'll end up as a very big star when the fuel starts to run out, a so-called supergiant star. And depending on how massive the star is, it could end its life as a supernova. It could blow itself almost to pieces, not by just gently shrugging off some of the outer layers of the star, but by a catastrophic collapse which effectively blows the star to pieces, except for a tiny piece in the center which gets crushed down to either a very dense object called a neutron star or perhaps even a black hole. A white dwarf is smaller than our sun. It's about the size of the Earth, roughly speaking. But a neutron star is a similar sort of mass, but now crushed down not to the size of the Earth, but crushed down to just a few kilometers inside. Very dense, a similar mass to the sun, but in a volume that's only kilometers in size. If that crushing effect of a supernova explosion crushes the central star even further, then we get a black hole from which not even light can escape. But one thing to notice is that although a star at the end of its life, if it starts as a cloud of hydrogen and perhaps a few other elements, it might end its life as a very small object like a white dwarf or a neutron star. But that's only a small amount of what the star originally was. A lot of the star has either been gently shrugged off as a planetary nebula or blown into the space between stars by the result of a supernova. In both cases, the material is recycled back into the space between stars. So stars are wonderful examples of recycling. Stars can be born from a cloud. They can go through a life which might be millions of years, it might be billions of years, but a lot of the material that's inside the sun, the star, will end up getting recycled back into a cloud which can make another star, which eventually goes bang or dies one way or another, and the material is recycled again and again and again. Our sun wasn't born purely from a cloud of hydrogen. It can't have been, because when we look at the Earth, what do we see? We see an Earth which is made of various elements, including silicon and aluminium and carbon and nitrogen and calcium and phosphor and all sorts of other materials, as well as metals. And they're a result of the stars processing, fusing hydrogen into heavier and heavier elements. So for those of you who remember your periodic table at school, this is an idea of what it looks like. Let's just dim it down a bit, otherwise it's a bit ferocious. So we've got hydrogen there, and if we fuse hydrogen together, we can make helium. In other words, we take individual nuclei, individual protons as it happens, individual nuclei of hydrogen atoms, fuse them together, we can make a heavier element. If we take helium and fuse it together, we can make heavier elements. We can make carbon and nitrogen and oxygen, which is just as well, because we, as carbon-based life forms, absolutely need carbon and nitrogen and oxygen and phosphorus and calcium and all these other elements for us to be, well, basically who we are. So basically the entire periodic table, or at least the first half of the periodic table up to iron, are all made inside stars during their lifetime. What about the heavier elements? Well, they can be made, but they are made either by sloughing off the outer layers into the interstellar medium, or more likely they're made when a star goes bang, when a massive star goes supernova. The heavy elements that were made inside the star gets redistributed and recycled into the interstellar medium, and heavy elements are made as well. So the silver, the gold, the lead that we see on the Earth is the result of a star coming to the end of its life and reseeding all of those heavy elements back into the interstellar medium. Let me finish in the last few minutes by thinking about what do we think is going on at the center of a galaxy. Well, we're not absolutely sure, but it appears there is something very interesting happening at the center of our galaxy and perhaps every other galaxy in the universe. For quite a few years, for the best part of 10 years, people studied what are the stars doing close to the center of our galaxy. And they deduced that the stars are moving in orbit around something. They can see the stars moving, but they couldn't see the thing around which they're moving. So just like planets are going around the sun, it's easy enough to see the sun, but these stars are moving around something, and yet we can't see what that something is. So one candidate, the only candidate that seems to fit the bill, is something very massive but invisible. We think it must be a very large black hole. So from years of studying how stars are moving around the center of the galaxy, we come to the conclusion that the object holding all of those stars in orbit in the center of our galaxy has a mass of 4 million solar masses. That symbol there, M circle dot, is just shorthand for the mass of our sun. Rather than talk about kilograms or tons, it's easier to talk about how big a black hole is in multiples of the mass of our sun. So we think there's an object of 4 million solar masses sitting at the center of our galaxy. As I mentioned earlier, we don't know whether that came first and the galaxy formed round it, or whether the galaxy has existed for a long time and then the black hole formed in the center. That's still an active area of research. But we do know there's black holes around in the cores of other galaxies because, for instance, relatively recently, an experiment was done where a group of astronomers observed what's going on at the center of a particular galaxy. The galaxy is labeled M87, and at the center of that galaxy there appears to be a very large donut. And right in the heart, we can't see what's going on. There's a shadow right in the middle there. That's where we think the black hole exists. And this donut is all the material, just like water going out of a bathtub, it's all the material that wants to get pulled in by the black hole, but ends up circulating around the black hole, waiting its turn to get pulled into the black hole. As it circulates around this so-called accretion disk, everything gets really hot and it emits a lot of energy. And that's what's being detected in these sorts of observations. So we haven't done the same experiment on all galaxies, but we think every galaxy probably has an enormous black hole at its core. If we look at individual images, like a Hubble image of a galaxy, we can be forgiven to think it's all very serene, almost like Gaia rotating slowly behind us there. A snapshot, of course, doesn't tell us how it's rotating. We can deduce that galaxies rotate very slowly over hundreds of millions of years. But a snapshot like that doesn't tell us that galaxies often interact with each other. We can sometimes take snapshots in which it's clear that galaxies are interacting. This one looks a little bit distorted and this one looks very distorted. They are interacting with each other. The gravity of one is pulling on the stars of another, and hence they are not beautiful spiral shapes. They appear to be somewhat more distorted. But we can only really understand, we can only appreciate the role of collisions and mergers of galaxies, not by individual snapshots, but by doing simulations that give us an idea of what the early universe looked like. And here we see, over a fraction of a billion years, galaxies are not static objects that just sit there to be photographed. They are dynamic objects. They are always interacting with each other. You can see in the center here two very big galaxies which just passed each other, and now they are about to merge together. There they go, passing through each other again and now merging together. Two galaxies are now sharing all of the stars that were originally in two galaxies. They're now in one bigger galaxy. As far as we can tell, that process has been going on for billions of years, and that is how galaxies evolve. They don't simply get born and then in isolation live out their lives. If they're close enough to other galaxies, they will interact with them. There will be a gravitational tug of war, and they will interact and collide and merge with other galaxies. That is basically an integral part of galaxy evolution. We think our galaxy, the Milky Way galaxy, has interacted with other galaxies. As far as we can tell, our immediate neighbor, the Andromeda galaxy, is going to interact with us. We are going to have a collision of our galaxy with our neighbor, the Andromeda galaxy. Not for a few billion years, no need to change your calendar ideas. It's going to be quite a while, but we think it will happen in a few billion years. The Andromeda galaxy is going to collide with ours, and much like we saw here, stars will be interchanged between the two. So, understanding galaxies and understanding stars, it's taken quite a long time to get to this level. It's taken hundreds of years of observations and decades of computer simulations, but we're now at the point where we can start to understand how galaxies formed and how they evolve, and how stars formed and how they evolve. And remember, the important factors are that everything came together in the early universe because gravity pulled stuff together once we had enough hydrogen to make all the stars and galaxies. We think there are black holes at the center of every galaxy, but we don't really understand why. And chicken and egg, we don't know whether the black hole came first or the galaxy came first, but it appears to be an integral part of every galaxy. And galaxy collisions are an important part of how galaxies have ended up looking the way they have. So if nothing else, hopefully you might be able to remember the ABC of stars and galaxies. Thank you all very much.